Greeting Chemistry 130 aspiring wizards. So today what we're going to be doing is taking a look at a demonstration involving some gas-filled balloons. So behind you, you see 5 balloons and they're filled with a variety of different gases. So what we have a nitrogen balloon. Remember that that's N2, a diatomic. Then we have a helium balloon. The third one is a hydrogen balloon, also one of your diatomics. In our 4th balloon, we have oxygen gas, yep, a diatomic. And then in the last balloon over here, we have a mixture of hydrogen and oxygen. And it's in a 2-to-1 ratio, which hopefully you remember from your stoichiometry. So what I want you to think about before I do the demo, here are the questions I want you to ponder. I want you to think about several things that you've already learned and then a few things that you haven't yet. So I want you thinking about the relationship between structure and function. So for example, what do you think about the relative positions of the balloons in terms of, you see some of them are higher, some of them are very heavy. Why do you think that is? Do you think it has to do with how much is in there, or maybe it's dependent on the type of atoms? So think about that while we're going through this. Another question that I'd like you to address is, what do you think will happen when I expose each of these balloons to a flame? Do you think that there will be a combustion reaction in each case? Do you think there will be no reaction? And why? Another question I want you to think about is, how do you think the structure of the molecules themselves affects the reactivity? Do you think they're related in any way? Do you think the number of covalent bonds that are present, or the position of the atoms or molecules from the periodic table, affects how they're going to react? And the last question I'd like you to consider is, do you think that mixing the gases has any effect on their reactivity? Like, does the environment matter? Should we be thinking about what chemicals are around the chemicals that we're working with? Does it matter? I bet it does. All right, I want you to ponder those questions and then we'll go ahead and do the demo. All right, so for our first balloon, we have nitrogen here. And it would help if you take a moment to think about where it is that you most commonly encounter nitrogen in your everyday lives. Because when we're thinking about what's likely to happen, as far as if a reaction will occur or if it won't, it's always good to try to connect it back to something that we know from our everyday lives. And of course, where I think of nitrogen is in our atmosphere, right? We've got about 70% of it in our air. So what I'm going to do is light one of these dowels and use it as a source of flame and simply see what happens when we introduce it to the balloon. All right. So let's see what happens. Wow, quite impressive. Now, if you're thinking about this logically, I hope you came to the conclusion that it's an awfully good thing nothing happened. Imagine if nitrogen were explosive. It's 70% of our atmosphere. That would be a problem, right? So it's a good thing that nitrogen does not combust. So that one, ta-da, that's the nitrogen balloon. And our second balloon, we have helium. So let's think about, what do we know about helium? Well, we know that it is a noble gas, and I hope that at this point in the semester you might think, well, the electron configuration of helium is a full closed shell in its valence orbitals, right? So, I wonder if that will have anything to do with its reactivity. Let's find out. So here comes our helium balloon. Yep, very predictably, the noble gases are very, very unreactive, exactly like we would predict they are. So the electron configuration makes a huge difference in what's going to happen with a lot of these balloons. Now, the other thing I want you to think about, as I referred to at the beginning of this, is why some of these balloons float and some of them don't. You'll notice, of course, that that helium balloon was pulling toward the ceiling, and our first balloon, the nitrogen, was down on the table. Why is that? it's not about the number of molecules or atoms in the balloon. It turns out that it's about the molar mass of each of those gases. So the density of gases is actually what affects whether or not they float or sink. It's the relative density to the mixture of normal air. All right, so let's take a look at our next balloon. For the third balloon, we have hydrogen, that lovely diatomic. Now remember that the first diatomic that we looked at, the nitrogen gas, did nothing. And so maybe this one won't do anything either. Maybe diatomic gases are inert. Let's find out. Not inert. So some of you may have heard of the Hindenburg. That is why it's a little dangerous to have hydrogen in a gigantic volume floating around where lightning strikes happen and sparks, etc. So hydrogen, as we just saw, is extremely combustible. Now, why is it that hydrogen actually reacted when nitrogen didn't? I want you to think about the structure of the nitrogen molecule versus the hydrogen molecule. Draw out the Lewis structure for a moment. And what you're going to realize is that that N2 molecule has a triple bond. All three of those bonds would have to break in order for that combustion reaction to occur. That takes an enormous amount of energy. This flame is not enough, and in fact, it's an endothermic reaction. The hydrogen balloon, on the other hand, has a single bond between it, and it takes much less energy to actually break that bond. And so we do get a combustion reaction. It's an exothermic reaction, as you saw. So it really matters when we're thinking about the structure of these molecules in thinking about their reactivities. And on to our next balloon. We have oxygen, O2. So we've seen that some diatomic molecules are flammable, some aren't. And let's see what happens with oxygen. We know that we see warning symbols all over the place in hospitals with oxygen tanks. So we might expect that this is going to be a pretty significant reaction. Let's find out. Well, that wasn't very exciting, was it? So maybe there's more to the story about why it is that we're warned about the presence of oxygen. Let's investigate that. Also, before we move on to the last balloon, I want you to think about the structure of O2. Remember that O2 has a double bond between it. And yes, that is significant here. It does take quite a bit of energy to actually break that bond. All right, and here's our last balloon. And so what we saw was that the hydrogen balloon did combust. It fully reacted, whereas the oxygen balloon really didn't do much that was very impressive. So you might think that, based on your logic, that now I've diluted my hydrogen, which was exciting, with the oxygen, which is not so much. So we might expect that this balloon won't actually be very impressive. So let's find out if our prediction is right. Well, that was impressive. So what just happened and why? Well, it turns out that that's the exact same reaction that happens when hydrogen exploded before. Hydrogen was reacting with oxygen in the atmosphere to make that big, beautiful fireball. What just happened here was that the same reaction happened, just much more quickly, because the oxygen was already present in the balloon. And so those hydrogen and oxygen molecules can collide and find each other much more quickly. And bang. So this is the reason that even though oxygen itself is not very reactive, not very explosive per se, it's very dangerous when it's mixed or nearby with other explosive or reactive chemicals. It's an accelerant. It's an oxidizing agent. It can, as you can see, lead to some pretty impressive explosions that get out of control very quickly. So it's always important to know your chemistry, to know what it is that's likely to happen and why. And it always comes down to the fundamentals. So I hope that you've been able to answer some of the questions that we've gone through today, and I hope that you enjoyed this demonstration.